notebook if you need the points. I'll also post a grade calculator. This is another thing. People have been saying, why aren't you keeping a running track of the grades on Compass? Well, you know that's not a good way to do it, I hope. I mean, that's like pre-election. Not pre-election. Did you ever watch the election returns where they show like when the count's coming in and there'll be 90% for one candidate and of course they'll already call it for the other candidate? It's not a good, math people should know that. Students like it, but people have been emailing me and say, why aren't you, we don't know what our grades are. What? You know what your grades are if you're mathematical at all, which basically if you know simple algebra, you know what your grades are better in this class than anywhere else. I give them to you exactly, always, and I tell you exactly what the formula is. What more do you need? But since some people are having some difficulty, apparently, I'll just do that formula for you, and you can put in what you need to, you know, your current scores, and I'll compute what you need to get on the final to achieve whatever grade you're aiming for, which is a whole lot more predictive value than your classes that give you, you realize that's not a good prediction, that running total, and why. I mean, think about it just, well, we can go into that later, but if anybody who doesn't realize that, talk to me. Okay. We're doing it in Stat 100 only because of popular demand, not because this makes sense. All right. So this is our chapter 42, and as we're doing our second non-parametric test. Now, the first one was comparing two means. And it was the non-parametric equivalent of a two-sample t-test. Now, what we're going to do here is just add another group. And what if you want to compare three means or four means? Well, then we can't boil it down to a single-signed difference, so we have to do ANOVA, like we always do, and compute either a chi-squared or an F statistic, right? And so this is the non-parametric equivalent of ANOVA. All right. Now, so the Kruskal-Wallis test is an extension of the Wilcoxon-Mann-Whitney to three or more groups. It's the non-parametric version of ANOVA for comparing group means. It has the advantage of not needing any assumptions about the underlying distributions. Usually that's the underlying normal populations that we assume with our ANOVA tests. Now, it starts off exactly like the Wilcoxon-Mann-Whitney test that we did previously. I have to pull up a different notebook to show you here. That we did in the previous chapter. You just did homework on that, so I probably don't even have to show you. It's probably very fresh in your minds. All right. But now what we're going to do is we're just going to combine the three groups into one ordered list. Here, for example, we did the two groups when we were comparing to see if these two versions of the exam were of equal difficulty. We just changed these values to ranks and then computed rank sums for each of them. Well, we're going to do the same thing here. So let's do that. So let's say we have three forms of the final, which is what I'm going to have certainly for Stat 100, actually 9, but for you guys, hopefully 3. I'm not sure if I can manage that, certainly 2. So let's say we have 3 forms of the final, randomly distributed to 16 students ahead of time. And this was the actual situation that happened a lot in Stat 100, where I wanted to see if they were of equal difficulty. And I only had 16 people. So were all 3 versions of the final equally difficult for all types of students? So here are the scores, let's say. And we just want to change these to ranks. So with 3 of them, I just said, okay, so I just took all of them and combined them into one ordered list. If you don't have to do that, it just made it simpler for me here. All right, so then I looked here and I saw 10 was rank 1, right? 60 is 4, 70 is 5.5, and 80 is 8, and 100 is 16. There's 16 numbers altogether. So I'm just going to replace these actual values with the numbers 1 through 16. Correct? And ties, as usual, that says 5.5, are given the same ranking. So 70 was a tie because two groups got it here, 70 and 70. All right, so let's do the same with the next group. And we'll start with 70 again. 50. Start with 50. So that's 3. Then we have 5.5 and 9, 10, and 13. And the last group is 20 is 2, 75, 7, 86. All right, so that's all done. And now what we want to do is get the rank sum for each group. So just sum these numbers for each group. So the rank sum for this group, just sum 1 plus 4.5, 1 plus 4 plus 5.5 plus 8 plus 16, and I got 34.5. Okay, so that's the sum for the group A. And now we'll do the same for these groups. So this sum, 3 plus 5.5 plus, I got 40.5 here. And here, when I summed these, 1, 2, 3, 4, 5, these are 6 numbers here, I got 61. All right, so this is all very much the same, right? No questions so far, correct? Because it's exactly what you did with just two groups. All right, now, again, if we want to make sure, we want to make a check here. So we want to check that, they 34 plus 40, 34, these three numbers sum to what? N times n plus 1 over 2. And because we're going 1 plus 16 is 17, that's the n plus 1, 2 plus 15, 17, da, 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 da. And we're doing that 16 divided by 8 times. So it's going to be 16 times 17 divided by 2, 8 times 17, which is 136. So you want to check that, just to remind you, 34.5 plus 40.5 plus 61 equals 136, and it does. Okay. So again, nothing new so far. So now, again, nothing new. How do you think we're going to compute the expected sum for each group? Remember how we do that. Okay, so since the null hypothesis is that these three groups were formed just by random division of the numbers, integers between 1 and 16 divided into 5, 5, and 6, that of course, the expected value, you wouldn't expect any group to be either above or below average, so the expected value for each group is just the average times the number of elements in that group, the sample size of each group. And that's what this says right here. This is the sample size of each group, and this is the average, right? The average of the numbers 1 through 16. So for the first group, the expected value for the, compute the expected values for each group. Okay, so here I said 5 times 8.5, right? So this is just, in this case, this is our sample size. And that's the average of the numbers 1 through 16, the overall average.
I mean, 1 through 17.
1 through 16, right? It's the average of the numbers 1 through 8.5. 1 plus 16 is 17 divided by 2 is 8.5 times 5. Yeah, average, okay, make sure, this is the right here is the overall average, the average of all numbers. The total sample size. And this number right here, that little n sub 1 right here, is the sample size for each group. Does that make sense to everybody? You got it? Okay. So we got 42.5 here, and so what's this one going to be? You can write it down for yourself. This is also a sample size of 5. This is a sample size of 6. And the average of the numbers 1 through 16 is, they're even numbers. So you can see there's not going to be a single number. So it's right in the middle there, between 8 and 9. There's an even set of numbers here, so it's going to be between 8 and 9, 8.5. 6 times 8.5, and this is 5 times 8.5. So 6 times 8.5 is 51, and 5 times 85 is equal to, it's the same thing, 42.5, and this is equal to 42.5 as well. So those are averages. Those are our expected values. And here we should write down, what are these? These are the observed rank sums. Observed are rank sums for each group. That's what we observed, and this is what we expect. So this is, we're going to look at the difference between the observed and the expected, but since we have 3 groups, not 2, what do you think we're going to have to do with all those differences? Because if we just added them up, I guarantee you they're going to add to 0. The positives and negatives are going to cancel out if we add up the differences. That's, by definition, they have to. So what are we going to do? Square them. That's what we always do, right? And that's why we have to have we can't use a z or t-test. We use a chi-squared test. Or an f-test if we didn't have counts. Now we have basically counts here. We're going to be using a z-test. The extension of a z-test to a chi-square test. Okay, 2 more groups. All right, so that's what we're going to be doing here. And it's going to approximate a chi-square as long as our sample size is big enough. Otherwise, we can easily figure out the exact probability distribution like we can do with any of these non-parametric tests. When you have a very small sample, you have very well-defined, easy numbers. You have your complete, they're always going to be the numbers between 1 and your total sample size, 1 and n, 1 and 16 this time. And we're just looking at the probability distribution of the sums of those numbers when you divide them, when you randomly divide them among 3 groups of size 5, 5, and 6. That's a very well-defined problem. You can easily do that. You can do the exact probability histogram of the probability of getting every possible sum within each group. And that probability histogram approaches the normal chi-square curve now, because, right? The chi-square curve, because we're testing the null, and we're testing the probability of what those rank sums. We have to find a test statistics that captures what we want to find out, and what we want to find out is, are there any differences between the 3 groups? So we have to use a chi-square distribution to capture that test statistic, because we have to count all 3 groups and we have to square them. All right, that's the idea. It's the same idea we've been talking about all semester. So back to it. So the test statistic, it's called H, follows the chi-square distribution with degrees of freedom equal to, chi-square always is the number of groups minus 1 for this type of problem when you're testing this null. All right? And the null is that there's no differences between the 2 groups. And the alternative is that there are. All right, now you look at the statistic, and at first, well, this part probably looks very similar to what we said the standard deviation was on the, for our last one. Remember, let's look for our last. It's right here. this is the standard error right here. Doesn't this look almost the same? Remember, chi-square is the ratio of two variances, so you have the observed minus the expected squared in the numerator, right, the sum of that. And the denominator, this is a standard deviation, we'd have to square that. So imagine squaring that and inverting it, because it's going to be in the denominator. We're just pulling it out because we're summing, right? And we're going to get something extremely similar to that. You flip that over and square it, and you'd get, and now these are for two samples. Now we have three. So it's, the structure of it is very apparent, like a usual chi-square stat. And so that's what we're going to be doing. And let's do it. All right. So we're going to compute this chi-square stat. So as usual, it's going to be the sum of the observed minus the expected over the standard error. All right, so let's do it. So H is equal to 12 over, the sample size is 16 times 17. And now we're going to sum up three groups. All right, the observed minus the expected in three groups. So our first group, our observed minus our expected. Our observed is 34.5 minus the expected is 42.5. That's what? -8 squared, -8. And what goes in the denominator here? This is the sample size. All right, now we'll do the next one. The next one is 40. Our observed is 40.5 minus the same squared over 5. And that's -2. So for inside here, I'm just showing you that we have to square them, because if we didn't, what do we have here? -8, -2, and the next one has to be +10, and let's just make sure it is, over 6, because that's its sample size. And so the difference here is what? 61 minus 51. Observed minus expected. So that works out. I'm just going to write that over for you so you don't forget that. The sum of the deviations before you square them is always 0. So let's just write that so you can observe, not forget it. So here we have -8, and that's, we'll square it. And here we have 2, and we square it. And here we have 10, and we square it. And I did that, and I got 1.344. Now that's my chi-square statistic. All right, so that's going, remember this is an approximation. We have a small sample size, and we're approximating it with this chi-square. Yes? Yeah, of course. See, here I tell you to check it, and look what I do. I said these two have to add up to 10. Thank you very much. Okay, let's do our usual, especially before an exam, you get an extra credit point on the final, okay? Because I don't want any mistakes in the notes. Everybody here probably gets it, but there's going to be people who are watching this, and they're just going to be scrolling through to fill in their notebook, and they're going to get it all screwed up. Maybe they should, but it's nice to correct it here. Let's serve them right, if that's what they do. But we're being nice. Okay. So that's good. And so now, all right, so this is distributed as a chi-squared with how many degrees of freedom? How many degrees of freedom do you think? 2, because we have 3 groups and it's 2 degrees of freedom. So you might forget what the chi-square distribution looks like, and why don't we go to, do we have an empty page here? No. Just going to write on this. All right, so let's continue this. I don't have much room here. And we'll just say this is distributed. Okay, we want to compare our chi-square stat with how many degrees of freedom? 2 degrees of freedom. 3 minus 1 degrees of freedom. Number of groups minus 1, that's where you get the 2 degrees of freedom. Our chi-square stat to, why don't we do the critical value. Let's see, why don't we go to the back of our book first and see what we want to do. We have 1.344. We usually compare it to the critical value. That's going to have a star there, that critical value, with 2 degrees of freedom at, we'll just say alpha equals what? Usual? P, do you want to do 5%? We're never going to make it. Do you remember that the chi-square is statistic is centered at what? It's expected value is its degrees of freedom. So this is like is going to be close to 50. This is nowhere near far enough out on the tail. But let's just do, we'll say it anyway. Pretend you didn't know that. At alpha equals 0.05. We're going to need a bigger chi-square to reject this. So let's look in the back of our book and see. And here's our chi-square. We have 2 degrees of freedom. Look, it's not even big enough to have 30% in the tail. And here, right here, is the critical value. We'd need 5.99, a chi-square more extreme than that to reject the null. We can't even reject it at 30%. Okay? So let's just write that down. So compared to chi-square, which is equal to 5.59. Certainly cannot reject the null. I can just show you right here. We can just put this right here. Okay, we can draw the picture. So just remember, with 2 degrees of freedom, it's not going to be very symmetrical. Chi-square is always positive. So it's going to look like this. It's not going to start looking like the normal curve yet. And what we saw, this critical value, means that right here at 5.99, that's the chi-square critical value at 5%, which means this right here is 5%. We are way up here at 1.344. This is drawn, should be to scale, so 1, 2, 3, 4, 5, 6. We're about there. So we're at 1, this is our chi-square stat at 1.344. So our p-value is huge. So RP, I looked it up previously. RP, this, our actual P, all that. RP is equal to, you wouldn't know this unless you looked it up on the table, the P calculator is 51%. All that area. Why am I doing it like that when I have a pretty highlighter? RP, this is what it is. This is 51%. And this right here is where we want to reject it. This is so, I mean, these p-values come up all the time. You've got to, this has got to stay with you forever, because I won't let anybody leave my class without understanding p-values. It would be every single job interview that anybody, I can just tell them they're going for a job interview. I say, they're going to ask you what a p-value is, because nobody understands. But you're going to get that job because you're going to know really easily. You're just going to, it's going to come intuitively. I mean, that's always what happens. So you're going to know it. Okay. And don't ever say, this is a surefire way to get rejected. Don't ever say, oh, P is 5%. They're going to look at you like, that's what you remember? No, you don't get the job. You don't want a job at a company that acts like that, that would accept you after you said that. I would never hire anybody who said that. And I don't think anybody, you don't want to work at some dumb company that would say, oh, good. No, you don't get hired. In fact, I don't know anybody who's gotten hired when they say, I usually ask them, well, what'd you say? I said, well, uh-oh, not going to work. Okay, so this stuff is, and it's for good reason, because this is how, for now, whether you like it or not, this is how people are making decisions about things. And I hope you realize it's arbitrary, but that's part of understanding what a p-value is. You set it where you want to set it. But the convention is 5%. You should at least understand that. So I just trying to show you what it means. It means that if these groups let's do it in the context of this example. If these exams really were different, if the null was true, and they were really the same, this is the important part. If the null was true and they were really the same, then we'd see such a big difference. Remember, these are the differences from what we'd expect. We'd see such a big difference. That's what's making our statistic go out far here. If these differences are large enough, then we're saying when the null's really true, when there are no differences, it's beyond a reasonable doubt. It's so unlikely. It's like if you're on a jury trial, you never know whether there's no way to know absolutely whether somebody's guilty or not. We're making decisions under uncertainty, but it gets so unlikely that we have to make a reasonable decision. And that's what it means by rejecting the null, that it's so unlikely to have happened. And look how likely ours is. So of course, we wouldn't think these exams. We have no evidence to think these exams are really different. All right. So that's the deal. Any questions on this? Okay. Now, why don't we move on to our next? You ready? You're set to do the homework on this, and it's not very long. I gave you a lot of practice problems, a lot of conceptual practice problems, too, for your exam, because we don't have much time to talk about this. And this stuff, you can get the conceptual problems on your own. That's what I love about this non-parametric stuff. It's all logic, and you can understand it all yourself. You don't need much guidance if you just think about it. So all the questions, many of the questions, the multiple choice questions in your practice problems for non-parametrics are just to get you to think about it. All right. Speaking of thinking about it, I don't know if I asked this one or not, but it's speaking of thinking about it. Okay. When does it make sense? What should you be looking at when you look at these numbers and decide whether you want to change them to ranks or not? Besides the fact that you don't, the usual things that you don't know the underlying distribution of the population, and you have too small a sample and you don't know it's normally distributed and so forth. I mean, what else should you be looking at? Why would you, I talked about it with the other, let's go back to this example, because this is the important takeaway from this course, way more than anything else, is thinking about what you're doing. So let's go back to the previous, do I have my notebook? Yeah. Okay, so let's go back here. And I don't know if you recall, but I said, we're comparing whether these two groups, these final given to Form A, to this group of students, and final given to Form B, are of equal difficulty. That's what I'm trying to figure out. And I said one reason why I want to change to ranks here is because this 11 is such a strong, it's going to have such a powerful effect. And if I think, making this exam look more difficult, somebody gets an 11, that's going to weight down the average a whole lot. Do I want to count it as 11, whereas I change it to a rank, it just says it's the lowest score. So it's equivalent to changing it to a 59. Do I want to do that? And I said I did in this case. Why? Because people who I don't think this person got an 11 because the exam was so difficult. I think he'd probably get an 11 if he took this exam as well. It's just somebody who left all of them blank because he had some other problem unrelated to the exam, psychological, or was clueless, or whatever happens to people who do that poorly in Stat 100. So I didn't want to use that. Now let's change the scenario. Let's change it to a medical example where this is, let's change this to even a 0. And let's say this is some drug, like a chemo or something like that, and these numbers indicate how many days or months or some time period that you survive after being given this drug, right? So if you survive one day, it might mean the drug could kill you, that it's very, very serious, right? Wouldn't we want to keep that and not change it to something like 61 days? We'd lose a lot of information, so we wouldn't want to change it to ranks, would you? I mean, let's say one drug could kill 1 out of 7 people. That might be the real distribution. And that's something we have to be, you absolutely want to know that. As soon as you give it to it, if the person survives 0 days or 1, that drug killed him probably. And you don't want to say, oh, that's the same as 61. I mean, it's 59, which is what you would do. You'd lose that information. So you absolutely don't just think about the math of it. Think about what you want to find out. That's the single most important thing I can teach you is don't ever just turn into an automaton machine and say, oh, we have this is a real cool method to do, because you will end up making terribly wrong decisions, and that's the whole point of statistics. There's no other point to statistics except solving real problems. Really, there isn't. It's not a game. It's not a silly, it's something that this is the only tool we have to figure out what's going on in the world right now, quantitatively with data. And we've got to think about the problem. All right? So I just want you to keep that in mind. So always think about what you're trying to solve, what you're trying to do, and why that method fits with it or not. And not just in terms of the math, but in terms of what you're trying to figure out, why these numbers matter or don't matter to you and why. Okay, just want to make sure you got that information. Now let's go to our last one, and this is going to be super easy for you, and we're going to get out early, so you'll have time to ask questions or start the homework. Yes?
Can you use statistics?
Good question. Very good question. Can we use the U statistic here? Not really, because the U statistic is just used when there's just 2 groups. Who beat who? You know, you're just counting up the number of wins. So this doesn't really translate well to a U statistic, to the rank sums. So that's another reason why maybe people want to use rank sums more, because they're more versatile when it comes to other problems. So that's important to think about too. Okay? Great question. All right. Now, let's go to this one. And I think you're going to like this too. This is just a non-parametric way to do a significance test to test whether a correlation coefficient is different than 0 or not. So just a reminder, we're looking at the next page here. We've got, these are our 3 tests. So, and I summarized them here, so we're on this one right here. These are the 2 that we've done. So there's other ones too. I just don't have a chance to get to them. There's some that are even simpler than these that I would love to. We just don't have enough time. But I think if you understand these ideas, they'll all come pretty easily to you. All right. So now let's look at our last one. And it's the non-parametric version of the regular correlation coefficient. And what we're going to be doing is we're going to be computing a correlation coefficient exactly the same way we always do, except we are going to be replacing these values with their ranks, which makes it super easy because the numbers will be integers between 1 and however many pairs of points you have, however many points you have on them, right? So let's just go ahead and we can do it. So, so what it means is that if you have n x, y pairs, you are going to replace them with x and y values between the numbers of 1 and n. All your numbers, so in this case we have 7 pairs, so all these numbers are going to get replaced with integers between 1 and 7. All right, so let's do that. So I made it, I just put these in order according to the x variable just because I thought it would be simpler. So this is the lowest number, just second lowest. So the x's are already in order. So now all we have to do is order the y's. Okay, so this is number 1, right? This is number 2, 45. Is that the next? This is number 3, 4, 5, 6, and 7. Okay. So there we go. And now, I don't even know if you want me to do this, but if you would like to see the correlation coefficient computed between these 7 numbers, it's very easy. Maybe it's good practice because those of you, we have some time, those of you who weren't in Stat 100 might forget how to do this. So here's your x values, and we're just going to, so the first pair is 1, 2, 2, 1, 3, 4, 4, 3, 5, 7, 6, 5, and 7, 6. Okay, so remember what a correlation coefficient is, which is what we want to get. The correlation coefficient, we're going to call it R, and in this case, we're going to call it RS for Spearman. The regular R would be to list our actual values here and do the same exact thing. But this is replacing them with integers, so it's the correlation coefficient for the Spearman. Yeah. Oh, yeah, thank you. I have 2 7s. Is it you? Do you get a second one, the same person? 2 extra? Is that you or is it somebody else? That's 2 for you today? Is it you last time too? Yeah. And yesterday? Not, I mean, the day before? No, okay. Okay. Well, thank you. Step up if you want an extra credit. Don't get all to her. Okay, so now what are we going to do? So, okay, so this is the rank. The R is just the sum of the products of the z-scores divided by however many there are, so the average of these products. So that's what we're going to do. So these z-scores, so we'll get those, and so these z-scores, remember what a z-score is. It's going to be, so z of x is going to be x minus the average of x over the standard deviation, right? So let's do that. So the average is what? And these numbers are the same, so y bar also, the average of these has to be 4. And we're going to say the standard deviation of the x's and the standard deviation of the y's. Do you want me to just tell you? These are very easy numbers. If you're rusty on how to compute a standard deviation from scratch, I can go through this extremely fast. I chose these numbers, so they're very easy. I might as well do it. It won't take but a minute. So I know this is 2, but I'll show you how I got that. Okay? So, all right. So what is the standard deviation? You all know. The standard deviation, what do? You take the deviations from the average for each number, right? The deviations. And then they sum to 0, so you have to square them, right? And then you sum them all, you take their average, and then that's the variance, and then you square root them. So these numbers are very, very easy, so you can do this pretty much in your head because you can look here and you can see the deviations would be what? The deviations, excuse me, 4, let's just do it for this one. So deviation 4 is at the average, so it doesn't deviate at all. I'm just subtracting 4 from each number. But you can see 1 is 3 below the average, 1 minus 4. Okay, and 7 is 3 above, just the deviations from the average. This is 2 above 1. So there's your deviations. Okay? Those are your deviations. I just put them here because it's easy. Okay, so then when you're computing this, what are you going to do? You're going to take the square root of what? Each one of these squared, so that would be 9 plus 4 plus 1 plus 0, and of course these are the same thing, plus 1 plus 4 plus 9, divided by 7. And that's 28 divided by 7, which is 2. So that's where I got that. And of course, these are going to be the same because they're the same numbers. So now we're just going to do our z-scores. And what is our z-score? It's the deviation from the average, which is -3, over the standard deviation. So this is -3 over 2. This one's -2 over 2, which is -1. This is -1 over 2. This one has z-score 0. It's right at the average. This is 1/2 a standard deviation above, 2 over 2, and 3/2. So that is our z-scores. And of course, they have to sum to 0 because these deviations sum to 0. These always sum to 0. All right? And now, these are the same numbers, but just in scrambled order. So the 2 is actually the -1 right here. Right? The 1's the -3/2. The 4 is right at, the average is 4. The 3 is -1/2. 7 is the biggest one. 5 is 1/2, and 6 is 1. And just make sure they sum to 0 too. They always sum to 0. Okay. And now, okay, so now what do we do? So notice why this makes sense. When you're doing a correlation coefficient, you're going to have a positive correlation if above average numbers pair up with above average numbers, right? Above, these are both above. Once you put them in z-scores, you have to get a common measuring stick between the two. That's what this does, a common measuring stick. How can you tell if something's correlated unless you get the common measuring stick? That's what you're doing with this, yeah?
Should they be symmetric? So like should the -1/2 be above the 0?
So the -1/2 is right. No, because the -1/2 refers to 3. I scrambled these. They're symmetric here. See, that's the whole point. I scrambled these. So, yeah. All right. So, when you're graphing them, like this is the common measuring stick, the z-scores. And so it makes sense when you have a positive correlation. When you have a positive correlation, just want to draw a little picture here. Okay, so they're going to be above average scores in both x and y in this quadrant are going to be associated with each other in both x and y, and below ones. So when you take, like these two are below average, so they're in this quadrant. This is in this quadrant. This is like, see, and then when they're above average in this quadrant. So this is overwhelmingly you can just see it's going to be positive. It's going to have a positive correlation. Negative correlations happen when you take the product of these and you get a lot of negative numbers that outweigh the positive ones. Okay? Oh, did you see that? If you're there. So that's all we're doing when we take the products. It's just an easy way to remember how the logic behind the correlation coefficient. I'm just teaching Stat 100 stuff because we have some time. This is what those of you in Stat 100 know this, I hope, like the back of your hand. All right, so now, those of you who've taken it. So now we're just multiplying these and we get 3/2, right? 3/2, these are positive. 0, 0, 3/4, and these are going to be positives as well. 1/2 and 3/2. And we're just going to add those up and take the sum. Okay? So we add all those up, and they go over here, and we add them all up, and I'll just do it here. So I add them up, and I got 5.75. That's the sum. But we want the average, so we have 5.75 divided by 7. And you get a very high correlation coefficient, and you could just graph these points to see. Super easy to graph, and you can see that you're going to get a very high correlation coefficient. So we really don't, you'd think, well, why are we going to test whether it's different than 0? That's so high. And the null hypothesis says that, yeah, in the population that these were drawn from, the correlation is 0, right? The correlation is 0 in the population. It's like just random points, right? That's what the null is saying. But since we only picked out 7 points, well, 1, 2, 3, I mean, pick out 3 points, of course you're going to get could easily get a high correlation. We picked out 7. You know, maybe that's just the luck of the draw. Maybe if we kept going, it's going to get like nothing. That's what we're testing here. All right, so what's the likelihood of doing? What we're testing basically is that we're looking at the probability distribution if you randomly paired up integers between 1 and 7 with each other. what is the chance that you would, and compute the correlation coefficient for each, all possible correlation coefficients, what's the chance you would get that extreme a value in either direction, because we didn't know which way it would go. It should be a, two-sided test. All right, so you could figure out the exact probability distribution and use tables, but why don't I show you how? I mean, we know that will approach approximately a normal distribution. So with expected value 0, and this is the standard error. It's somewhat easier than our other one because we know we don't divide by 2, n minus 2, because we know the standard deviation here of this. We have a better estimate of it. All right, so let's do that. So here we have our observed is 0.85 minus 0 over 1 divided by the square root of 6, because our sample size is 7. And I got 2.05. So I'm going to mark that on this curve. 0's in the middle. I'm going to mark 2.05 and negative 2.05 and look in the back of the book. And we know it's going to be it's two-sided. So let's see. 95.96. 1.96, it would have been exactly 5. But we're at 2.05. So we have 96% in the middle. So our p-value is right there. And find the p-value. We don't divide, right? Because we want both tails. Because I didn't specify a direction. So the conclusion is what? At the 5% level, we reject the null and conclude there's very good evidence. We're not sure, but there's very good evidence for a non-zero R in the population. I can't draw a rho. We were supposed to use the Greek letters. A rho looks too much like a P for me, so I'm just going to say non-zero R in the population. That's the Greek letter for R is confusing to me because it looks too much like a P. Okay? Now, let me see what we have next. We have all these practice problems. I think these are pretty much very similar. People like to work things out on paper. Some people prefer that. So I think these are really similar to the practice problems online. I hope I added more online. Did I? No, there are more ones online. Okay, but these are similar to what you did for homework already. And this is very similar to the homework. This is very similar to the homework. And this has some practice. This is some of the conceptual problems for your Spearman rank correlation coefficient problems. There aren't going to, I'm going to try to divide the test up. I'll give you the exact breakdown of how many questions there are going to be on each thing after I write it. But since you've never been tested on the non-parametric section, it will be weighted more than the others, but since it's such a short section, it'll probably be shorter than some of the exam 1, 2, and 3 material, but it will be weighted more than, it's going to be weighted enough to count it as if you'd also had a test on it. It had been included in a test, if you understand what I mean. So, and it will be about 2 hours long, your final, and I'm still debating whether to make it Scantron. Any ideas about that? I could make it Scantron, or I could make it an actual paper pencil test like you're used to. We can still grade it, but if anybody has strong feelings about that, I should have put that on a survey, but Anybody want to speak to that? Raise your hand. If you, I need eye clickers because I can't tell what you're thinking. But lots of times people don't respond. But how many people would prefer a Scantron? I just want to see a show of hands. How many people would prefer this type, like just the exams you've been getting on? All right, done deal. That's over. Yeah, we have enough time to do it. I agree, because I will be able to, I learn a lot more grading when I can see what you're doing. It helps me, but it's just, I was just thinking with a Friday final, that last final, it's hard to, Thursday night, we won't be able to grade it until the following Friday. That's going to be hard. But we'll do it. It's not that many people. So, all right. So how about office hours? Because I won't see you again until Tuesday. So you know what you have to do. I'll write up some study guide questions for you. I mean, not study guide, how to study for the final. I'll write that up for you, so you'll have that for the weekend. And everything's posted that you need to do, and we'll have extended office hours maybe next week, like on reading day, probably. Okay, that's it. Hey, we're finished early. Good.